what we want to do now is show you how to generate the uncertainties on our measurements. So when Excel, when you perform a linest function in Excel, you can get the slope, the intercept, and the uncertainty on both. And what we want to do at this point is show you how to get these two numbers. Okay, how can Python give us those two numbers? And we're doing this from scratch. Remember now, as a word of warning, there are routines that are already built in, so I don't have to go through this whole process. Okay, I don't have to go through this whole process, and we'll show you how to just call an already written routine here in a bit, but this shows you the back end, right? And also this also shows you how the calculations are done, what the calculations are doing. You don't necessarily have to understand everything at this point, but it is insightful to see that you can generate this yourself. So to get the uncertainties on the slope and the intercept, we have to calculate a quantity first that we call the variance. And the variance you can think of as the deviation, or perhaps a better way of thinking about it is kind of an average of the deviation of those squares. So remember when we talked about having data points that lied some distance away from our best fit line, what this equation is doing is taking each of these deviations and squaring it, and that is what this term is, and then summing all of those up. So your y elements are going to be subtracted from your model, right? So your model is the m times your x elements minus your intercept. And then this is your individual data points. And so you're going to take each data point, calculate the model at that x value, subtract the two, and then square it so that everything is positive. And in effect, it's this function that you actually minimize by taking derivatives that gives you this set of equations that we use to calculate the slope and the intercept. All right. Now, that's not strictly the only parts in that function, but this is the meat of what you actually do. This is the meat in that function. Now, this 1 over n minus 2, the denominator here is what you're actually dividing by. So I say that this is an average because you're summing things up and then dividing by a number, right? Now, it's not strictly an average because you're not dividing by the total number of elements. You're dividing by the total number of elements minus the number of parameters that you're trying to fit. So we are trying to fit the slope and the intercept, and as a result we're going to subtract that number of parameters from our total number of elements, and what's left over, right, this n minus 2 quantity, what's left over is known as the degrees of freedom. Now, one caveat: this assumes that all of your uncertainties on your y values are the same. So we basically have a situation with uniform error bars on our y values. Now, this is not usually the case in higher level physical cases, but for the moment, to show you how Excel does things, this is what's happening. So Excel says, okay, I'm going to assume that each individual measurement has essentially the same error on it, and if I do that, then the individual uncertainties factor out of the derivatives in these equations, and they basically cancel out, and you don't have to worry about the individual uncertainties when they're the same. So then you take this variance and you do something with it to calculate the uncertainties on the slope and the intercept. So to get the uncertainty on the slope, once you have the variance, you multiply that by the number of elements and then divide that by the delta function that we calculated. And then to calculate the uncertainty on the intercept, take the variance, divide it by delta, and multiply it by the sum of the squares of your x elements. So if I put these in, right? So if I put these in, let's go ahead and say, all right, sigma slope, and I'm just going to abbreviate this as SL for slope. So sigma slope, this is going to be np dot square root time n time. Actually, you know what I need to do first? Let's calculate the variance. So this is going to be 1 divided by n minus 2 times the sum of y minus the model, right? So I'm going to take each individual y value. So this expression here is because y is an array and our model is an array. What this is going to do is say, okay, for each y value, I'm going to subtract each model value, and then I'm going to sum those up. But I need to square them before I sum them up. So I actually need two parentheses here, and I need to square the inner parenthesis first. So this is telling Python to take each individual data point minus the model, square that, and then I'm going to sum all of those up. All right, so this is our variance. And now I need to multiply by my variance, and I need to divide by delta. All right, and the sigma on the intercept is going to be np dot square root variance divided, actually, and let's multiply first by the sum of x squared and then we will divide that by delta. Okay, and let's now print the slope. We don't need to print the slope, we've already got that. So let's print sigma SL and sigma IN. All right, and let's see what happens. Okay, there we go. And you'll note that these are the same values as given in Excel, and our plot here has the data and the trend line agreeing with Excel. Now, personally, I would probably not do this way. Okay, the formatting of the way this is printing out, I would not do it that way. And the reason being, pardon me, the reason being, you don't necessarily want to just keep printing off numbers, because then you have to keep track of the way things are. So the way that I would actually probably do this is, when you want to print text, you need to enclose your text in quotes. So I would probably put something like the intercept is, and then you need to join that text with your value with a plus sign. Okay, so this is going to, and actually, it'll make more sense to put a space here, because then it'll give you a space between your statement and the value. So let's just make sure that that line works. Oh, what's the syntax? Do I need to put this in a string? Let's see if that works. Yes. Okay. So what this is doing is saying I can't add strings and numbers. I can't add just regular text and numbers. So you actually have to convert your value of your number to a string. And a string is just a set of letters. Okay. Or numbers. It could be numbers, but this is basically when you put something in string form, you're basically telling the computer to print whatever I type. Okay, and this will help you keep track of what values are what. And so then I would also put the uncertainty on the slope is and the okay. Oop. All right. So this will allow you to kind of keep track of what you're doing, right? So instead of just reading numbers and trying to remember what order you had them printed in, this will allow you to keep track of those. And there's one more thing that I will show you how to do very quickly. And that is how to add axis labels to the plot. So this way, because of course we are in physical data. Now we didn't say what our x and y values here were, but for the moment let's just assume that these are times and positions. Okay, these are times and positions. So what I'm going to do, the command is plt.xlabel, and then I have to put it in quotes, and I'm going to say time, and I'm going to denote that the units are seconds, and plt.ylabel, and this is going to be position in meters, and whatever you type here will be displayed exactly as you type it. Okay, and we run that, and now you can see that the plot has axis labels, and so this allows whoever sees your plot to know what you did, what units are you in. There are myriads of ways to adjust your plots. There's really no end to the way you can format these. You can adjust what tick marks you see. how you want the tick marks displayed. You can adjust the font, you can adjust the font size, you can adjust the marker size, you can adjust the thickness of the lines. There's just literally no end to how you can format these plots. But just to generate a basic plot and have it to put in a report or something of that nature, this is the quickest way to do it. All right, we will end this video there, and we will in the next couple videos show you how to do this much more quickly. But I wanted to show you how to do this because this is very important. This is how you actually would write a routine. This gives you an algorithm that you can use, and once you verify that it works, you've got it for all time. You don't have to trust that someone else may have made a mistake. So there's value in seeing things from the ground up, but we will show you how to get this with a pre-built function in Python, because we also want you to, in the long run, be able to work smarter, not harder, and that will speed up the rate at which your productivity is able to be produced.